I'm going to move my camera so when I'm looking at the presentation, it looks like I'm looking at you instead of looking sideways. Does that look like I'm looking at you? I can't even see.
Yeah, that's okay.
Okay.
It looks good.
Yeah, because I got two screens and it depends on where I put the camera, who I'm looking at. So you're over here.
Okay, and the presentation is in the other side. I
Yes,
get it.
I'll look over here most of the time. So. Let's see, have we got a quorum yet? Okay, I'll go ahead and start then.
Okay, it's recording already.
Okay. Oh yeah, we've probably been recording for a while. Rick will have to cut that off.
Okay.
Okay. Good morning, everybody. Okay, welcome to the next lecture. Let me get my pointer turned on. Here we go. Let me give a quick review of where we were the last couple of days. Just remind everybody, we just emailed around all these slides so you can have copies to follow along if you like, if the internet connection gets too slow or something, or if my computer dies again. But just very quick, everything we're talking about comes this very relatively simple formula. It looks complicated here because of the formatting. Okay? But the basic question is, if I have a point charge sitting someplace here at a position r prime, here's the origin of your coordinate system. So there's a point charge at r prime, and my detector is someplace at position r. And I shake this charge so it accelerates back and forth. It radiates a field, and the size of that field from the point charge is given by some very simple things. The formula on the right, this is units. We don't care about that. Q is the size of the charge, just what is the magnitude of it. This is the distance from the point charge to the detector. Here's the speed of light. And this is the acceleration of the point charge. The perpendicular sign on the acceleration means that if I'm sitting up here, my eyeball is here, and I'm looking back at the point charge, I can only see the accelerations which are perpendicular to the line of sight. If it's accelerating back and forth at me, I can't actually see that. I only want that part of the vector. And like when we see starlight, which comes a long distance across the universe, as we're really looking back into the past because the light has to propagate across here. We need to, what we're witnessing when we see the light that gets to us is the acceleration which actually occurred a little while ago, whatever this propagation delay is. So this is called the retarded time. It's just the actual time minus the distance between the charge and the detector divided by the speed of light. So the only thing which really matters in all of this is the acceleration at that point charge. The reason that's important for scattering, of course, is that acceleration will be caused by the incident wave coming through. In the last couple of days, we went through a fair amount of algebra to show that the scattering cross-section is given by a product of two terms. One is units. It's this Thomson scattering length, also known as the classical radius of the electron. And the next is the scattering amplitude, which is just the Fourier transform of the number density of electron charges. So this has units of, say, electrons per cubic centimeter or something like that. And it just tells you where all the charge is. And then, of course, there's the scattering vector. For the special case of a crystal, what I called A, the scattering amplitude before, we write as the crystal structure factor. It's the same thing. And it factored into three terms. The F sub j's here were these atomic scattering factors. So I model my system as atoms in a unit cell and then many unit cells. So the Fourier transform factors. And so this is the Fourier transform of the atom, the atomic scattering factor. This is the phase term, which tells me where the atoms are in the unit cell or the molecule. And this is my lattice sum, where I repeat this thing over and over again. And And so this is the entire structure of my crystal. For our mathematical convenience, yesterday we were talking about the reciprocal lattice. We defined a new set of vectors. They're called the reciprocal lattice vectors. I use these for them. And they're generated by these functions over here which are the real space lattice vectors. And so there's this cross product relationship where B1 looks like A2 cross A3. The B2 looks like A3 cross A1. B3 looks like A1 cross A2, and so on. The 2 pi is for convenience later on, as is the denominator here, which is just the volume of the unit cell. The key feature of these guys is that A1 and B1, when I got them together, you can just see if I check that if I dot A1 times B1, I'll get an A1 dotted into this cross product. Everything divides away, and I just get a 2 pi. So A1 is parallel to B1, and the overlap is 2 pi. But A1 is actually perpendicular to B2 and B3. And then similarly for the A2s and A3s. So the simplicity is going to help us a lot when we, later on, when we collapse all of our sums and so on. We came up with notation for lattice planes and Miller indices. In real space, the lattice is achieved by taking integer numbers of either A1 or A2, and I get all of my little lattice points here. The lattice planes are just imaginary planes going through rows of atoms. And I've showed 2 different sets of planes here. The indexing is not obvious, but if I put an origin here and I ask, where does the next lattice plane come over? It comes in here at the half position. So A1 over 2. So this is the 2 direction. The intercept up here is in the 1. So this is the 2, 1 plane. There's a reciprocal relationship here. And I know that doesn't seem like the obvious one, but it's related to the surface normals. I went through this diagram really quickly yesterday. Don't worry about it. This is a hard way to understand it. Easier way to understand it was in terms of Bragg's law, where we found that the intensity maximum occur whenever the scattering vector is equal to a reciprocal lattice vector G. So this is some integer number of B1, B2, and B3. Okay? And if just some very simple algebra, I can show that this condition here is equivalent to Bragg's law here, which tells me basically when do I get constructed interference between the incoming wave and the outgoing wave. The lambda is 2D sine theta is the classical interpretation on there. We also talked about the Ewald sphere, which is another geometrical construction. Next, it just gives you a convenient geometrical construct to figure out when you'll have multiple peaks turned on, how many are turned on, or if you have a finite energy width or wavelength spread of your beam. Okay, so that was sort of the 30-second review of an hour of work yesterday. And so if you can refer back to the notes from yesterday or ask some questions later on. And today what we want to do is actually consider in real experiments, what is the measured intensity of these Bragg reflections? And so in beginning with the simple formulas that we derived over the last couple of days. So let's start with the crystal, where we're, for example, face-centered cubic structure here, and there'll be one set of atoms at the corner, or another set of atoms on the faces, and I can write my unit cell just keep repeating this group of 4 atoms over and over again. So if I translate the thing over to this corner, I get the next unit cell. If I translate up here, I get another one, and so on. So I can recreate my whole cell by repeating this little unit here, these 4 atoms, the 3 face atoms and the 1 corner atom. Okay, now one of the reasons you look at it, and I could have picked a smaller unit cell but it wouldn't have been cubic. My brain, I find working in Cartesian coordinates and cubic coordinates to be the simplest one to understand. And the only complication of choosing that is that my basis has more than one atom in it. But by choosing a cubic unit cell, I can make sure that the reciprocal lattice is also cubic, and it has the very simple lattice spacing of 2 pi over a. Okay? And that's really simple for my brain to understand. And so the reciprocal lattice vectors, the g vectors, all take the really simple form of 2 pi over a as a length, or reciprocal length, times hk and l, which is just the indexes of those hk's and l's are all integers. And that'll tell me where all of my Bragg peaks are. Okay. So if all the atoms in the unit cell are identical, I can calculate my structure factor really simply, because the atomic structure factor, if they're all the same, will just come out of my sum. And I'm just left with this very simple phase sum here, which I can just write out for the case of my FCC lattice. There's my corner atom, here's one face atom, another face atom, the third face atom. And you can see there are only 2 possible numbers that you can get from this. If hk and l are all even or all odd, that number adds up to 4. Any other choice of integers, and they add up to 0. So there's only 2 possibilities. Okay. And what you find is so that this thing, remember, up here we had every single hk and l were allowed for a simple cubic lattice. Now my structure factor is telling me that some of these hk and l's will have a 0 amplitude. That the structure factor will go to 0, so I won't actually see those lattice peaks. Okay? Okay? And the reason those peaks actually disappear is my earlier statement, because I picked a unit cell which wasn't the smallest possible. It was convenient because it was cubic, but there are other unit cells which are a little smaller, which would not have had all these zeros showing up. So this is so you don't really have to worry about which unit cell you pick, that it being the smallest possible, because the structure factor will actually zero out those extra Bragg peaks for you. And the computational simplicity of working with a cubic rather than a rhombohedral unit cell is significant. Okay, so now we need to figure out, we've gone through and how to calculating the unit cell structure factor is pretty straightforward. But now we need to calculate all those lattice sums. Let me go back a couple of slides. So we're back here. The unit cell structure factor we just showed is relatively straightforward. Now we have all of these lattice sums to calculate over here. So we'll work in the cubic system again, just for simplicity. Okay, and so we get that the lattice sum structure has this form, but we have assumed that these position vectors, which are indexed, are the locations of all the unit cells, have this very simple structure because of the lattice. So these are my real space lattice vectors, A1, A2, and A3. And so R sub n will have 3 integers. There's in there. And here just tells me where am I in defining this vector. So if we look at this in 1 dimension, we can look at this very simply. I can choose to number my atoms in my 1-dimensional crystal from 0 to n minus 1. And I have this simple sum. If you remember, on Monday, we evaluated this geometric series already. Okay, and you get a very simple closed form solution. And we look back through the notes. So I won't go through the math on that again, but we know exactly how to do this sum. So you can consider this a solved problem. We don't have to worry about it. But now I want to ask a slightly different question. That what we found there is that gives me my a very sharp peak. And so I really want to know is not what happens precisely on the peak where I can add things up and so on. I want to know what happens when I'm just close to the peak. So I want to do is sort of, and ultimately I want to get the width of the peak, and I want to, and the line shape and so on. So I'm going to rewrite Q instead of being H times A star. sorry, I've changed notation on you. A star and B are the same thing here. So this is a reciprocal lattice vector. And I'm going to have H plus a little tiny bit. So this is going to, if C was 0, this would just be one of my G vectors. So I'm just very slightly off of the exact condition of Q equals G. If I substitute that back into my lattice sum expression, and I get this simple formula that we derived the other day. It's kind of like sine ratio of the sines of the sine of n pi c or the sine of c. Okay. So the absolute value of this sum is simply sine over sine. And if you then look at this in the limit of c going to 0, you'll find that the expansion of sine is just the argument. So sine of x looks like x. And so this, the numerator looks like the sine of nx divided by the sine of x. Divide the x's out, you just get n. On the limit when c goes to 0, this is the height of the peak is just n. So the amplitude of the peak is n. And we saw before that the full width at half maximum is approximately equal to 1 over n. So the area of this amplitude is equal to 1. And so if you approximately equal to 1, if you actually do the integrals exactly, you'll find out that it's exactly 1. So as n becomes really large, the width narrows and the peak grows, keeping the area underneath it constant. And that's basically the behavior of a delta function. And so it turns out to be mathematically one of the representations of the delta function. And so in the limit of n going to 0, the scattering amplitude of this lattice sum goes to a delta function. And that's the key result for this slide here. What it's going to allow me to do is work in an equivalent form. And I'm going to be a little careful with my units here. So the structure factor actually looks like A star, or the reciprocal lattice vector, magnitude of it, times the delta function here. And the A star comes from the change of variables in the delta function. Don't worry about that at the moment. It's just units here. And you can, this is actually algebra. And instead of delta C, we have delta CA star. That's what's going on. So in a diffraction experiment, we're actually interested in the squared lattice sum. So if I square this thing, I get an n A star times this delta function here. If I generalize to 3 dimensions, it's really straightforward, especially for my cubic system. So instead of n now being the number of atoms in my linear sample, n is going to be the total number. I'm going to have a product of 3 different lengths, which are the 3 sides of my cube. That's going to become a volume. And then I have a delta function, which is now a vector instead of linear. So this is now the total number of atoms in my crystal, not any particular dimension. This is the volume of the unit cell in reciprocal space. Okay? And this is a 3-dimensional delta function. If I'm not in cubic coordinate systems and don't have don't have a cubic sample, I can't do this sum so simply analytically. However, the delta function character of the structure factor is going to survive as long as I have a large number. And here, n just needs to be a large number compared to 1. If you get up to a few thousand atoms in each direction, you won't be able to tell the difference. Okay, now let's apply this to the real world. So far, everything we've talked about was really mathematical samples. Either they were infinite in size, or they were perfect cubes, and I could do my sums exactly. Okay. But what happens if I have a real sample? And so what I do is we're going to start by working with making a real crystal, first treating it as an infinite crystal with one surface. Okay. Okay, so what we're going to find then is that surfaces create these things called crystal truncation rods. Let me walk you through this. Okay, start with what we just talked about, a 3-dimensional crystal, and it's infinite. And we just showed that the scattering should look like a delta function, and on the reciprocal lattice there'll be some, let's say, cubic lattice as it satisfies the Laue conditions, and at each lattice point there'll be a delta function which has an intense scattering behavior. So whenever Q is equal to a reciprocal lattice vector, we see scattering. And I can generate all of the reciprocal lattice conditions by using my reciprocal lattice vectors, A1 and A2, and so G11 would be here, G10 is here, G01 is up here, this would be G00, and so on. That's the two-dimensional analog. Of course, it's in 3D. Okay, and we also saw, thinking about it, that for a finite size sample, now my cubic one again, that the width of the peaks went like 1 over n. And then there was a sort of sine squared nx over sine squared x behavior. And so the scattering basically spreads out over reciprocal. So both the magnitude goes down because the total intensity under the peak went like the number of atoms. So that's getting smaller, but it also gets spread out over some more volume of reciprocal space. And that volume is inversely proportional to the size of the sample. So the sample goes to infinity, the volume goes to 0, as the volume gets bigger. In reciprocal space, volume gets bigger as the sample gets smaller. And so schematically what happens then is I see that as my sample becomes finite size, these delta functions broaden into these bigger spots. Okay, now let's do a different experiment. Let's imagine that rather than my sample being big, infinite, and then I shrink it to being small in all 3 directions, I'm going to cleave it. So I'm just going to chop it in half. What that effectively does is instead of having a circle here, I expect something to happen in just one direction, depending on where I chop it off. And so, in fact, what I expect to happen is to start to get a streak of intensity. If it was broad in all 3 directions, I would see a circle. It's only finite in extent in one direction. And this is due to the termination of that it would have been a delta function for an infinite crystal. Because I put a surface in, it terminates here and I get this streak. And that's why it's known as a crystal truncation rod. And it's basically a failure if you don't have enough terms in your sum for your interference to actually focus everything back onto the Bragg peak. Okay, so our goal in the next couple of slides is to figure out what is the actual form of that expression. Basically, we're going to, in the 2 dimensions, let's assume that the surface normal is in the z direction for simplicity. So I still have my delta functions in the x and the y directions. So let's ignore those for a second. But now we can consider what happens to the sum normal to the surface that would have created this delta function. So instead of going from minus infinity to infinity, I'm going to put the surface at 0. Now my sum is going to go from minus infinity to 0. Other than that, it's the same thing. And I can quickly flip this around by just letting n equals minus n and change the order of my sum, put a minus sign up here. But we already know how to do this sum. And that this is the same kind of algebra we did for the finite sum. And you get the very simple answer that it's 1 minus this term here. So I can do this sum exactly, okay, with this really pleasing result. And so I can go back to my original formula for the scattering factor for my crystal truncation rod. Looks like my original scattering factor, or scattering amplitude, I'm sorry, but it has this new term here instead of a delta function. So that these delta functions are still up in here, but the one in the z direction is replaced by this thing here. If I calculate then the intensity, I have to take the square of this thing. So I get my original scattering factor times this times its complex conjugate. If you multiply this out, you see that's 4 times the sine squared of pi over L. I plotted it over here. So what this is the scattering vector perpendicular to the surface of the sample. At 0, this would actually be either forward scattering or you'll get some finite reflectivity. So what happens near 0? So this is interesting. We'll talk about that a little later. So A here is the scattering amplitude from a single layer. And then when I add up all my layers, I get this really beautiful set of streaks here. So that it's not a delta function in the z direction. It's got this 1 over sine squared behavior that we saw before. And it's really quite beautiful behavior. Now we should be a little cautious here. That our fundamental approximation was of single scattering and so on. And that means that most of the X-rays have to go right through the sample. They can't interact and so on. When we get really close to the Bragg peak, the peak of the Bragg peak, you'll see that experimentally we can get the reflectivity of the crystal as 1, which means that every single X-ray is reflected, and the kinematic approximation breaks down. So right in the center here, there'll be a breakdown of our kinematic theory. That can be dealt with the dynamical theory of diffraction. I'm not going to talk about that in this series of lectures, but there's this in this little tiny region, and basically within the half height, right? So this is a log plot. So if I go from here to here, if you're right in this little bit, we have to use a different theory. All of this stuff out here is perfectly well described by this kinematic theory we've been talking about. Now, it just turns out this is phenomenally useful. And let me give you a couple toy examples here and then a real example. So if we want to, you can ask the question then, what happens if the surface layer is slightly different? So I have my truncated crystal, but then I put one more layer on top of that that's a little bit different. So here's my perfectly truncated crystal, but then I add one more layer. In this case, I'm just going to dilate. I'm going to let my top layer be slightly enlarged or compressed. And I can just put that in. So if I assume the layers are exactly the same, the A's are the same, and I do this by saying, well, there's another, it's going to be displaced by L, the distance. That's my other phasing down here, same as this L. And there'll be a little tiny bit Z, which is the fractional displacement of the layer. Okay. So what I've plotted below is I assume a 5% shift. So if this lattice constant is just dilated or compressed by 5%, what happens? You can see if I expand it by 5%, that's the red curve. Well, first blue is the original one coming through here. But if I expand it 5% in this region, it's suppressed. Remember, this is a log scale, so this is a big effect down in here. All right, and on this side of the peak, it's enhanced. If I go out to the even order peak, it's reversed, where this part of the peak is here it was suppressed and here it was enhanced. You can see that, very characteristic. So if I flip the sign and go the other direction, so now I'm compressing the layer, you can see it's just the mirror image. So there's this huge signal out here, which is very sensitive at the level of just a % or 2 expansion or dilation of the lattice constant. You can see that. So if I go and consider, here's a graphite, a good example of a system. These are real numbers now. And there's the same calculation where in black is the undistorted graphite structure. But if I either compress or dilate the graphite structure, you get the magenta and the green curves respectively. And you can really see this difference in the, this is almost an order of magnitude change in the scattering. So it's very sensitive to the very small displacement of that layer. So we can use that to study things that a lot of you will be interested in, things like the surfaces of crystals at electrochemical interfaces and so on. And to give you one example, I'll go through really quickly is some work that Professor O'Brien and I did several years ago on the surface of strontium titanate in an electrochemical environment. And when we started, people actually knew a lot about the surface of strontium titanate in vacuum. and it's shown here with the references. And the strontium titanate is a perovskite structure material, perfect crystal. You see it down here. When you truncate the crystal in vacuum, it gets a titanium dioxide double layer on top. What intrigued us at the time is that strontium titanate could catalyze the splitting of water using the visible light. And so it wasn't a great catalyst, but it was a catalyst. And so we wanted to figure out what was going on with that. And so the next set of experiments demonstrate this, but the basic idea is that the electron density, if you just integrate over here, plotted on the right, as you go out, you can see this kind of page here. So our crystal truncation rods basically tell us what is the average electron density as we go up. And so this kind of model can be calculated directly from the structure here. And so we did an experiment where we combined electrochemistry, some scanning electrochemistry. Next week, I think Professor Brunia will probably go through all of this kind of stuff. But the key thing I want to show you is down here in the lower right-hand corner are that depending on the applied voltage, we could actually measure the electrochemical current, what's told us about the oxygen reduction reaction, the water splitting, what was going on. And so we could turn the lamp on and off, and depending on the voltage, we could actually change an open circuit or with a driving current. So you can actually see the electrochemical response is different when the lamp is on and off. So one, we're getting photo water splitting, and two, it's controllable by electrochemistry. Okay? And so the question is, okay, how does strontium titanate do that? And so the experiment was relatively simple. We had an electrochemical cell, and the sample is sitting here. X-rays came in and out. We actually detected them on an area detector. So this changed. This is KF over here, and this image here is shown here. You can see there's a vast number of things going on in here, but we chose to work at the appropriate spot on that crystal truncation rod where we were sensitive, and we could see as the light went on and off, and the voltage, we could still see everything going on. So this is what our data actually look like as we scan through. We can track everything going forward. And then this is the answer. This is many years of work, so I don't want to go through it all. But the key thing you're seeing here is here's the reflectivity. We were just talking about the crystal truncation rods. Here are the Bragg peaks of the strontium titanate coming through. This is the 001 and this is the 002. And then there's three different curves here. One is the surface of strontium titanate in air. One is the surface of strontium titanate when we initially plunged it into the electrochemical cell at open cell potential. And then the last one is the structure of the strontium titanate surface after it had been cycled up to a voltage, back to zero, and back up again. So there's an irreversible transition between the original vacuum state, the initial plunge state, and then the active state. And it turns out this difference here corresponds to about a difference of factor 3 in the electrochemical activity. Okay? So there's a real structural difference if something happens. The work actually involved a detailed collaboration with some people doing joint density functional theory. Okay? And the answer is you see that the initial state of the surface actually looked like this, where similar to the original titanium dioxide double layer, you see here, when you cycle it up to voltage and come back, it goes through an irreversible transition where basically you deplete some of the atoms coming out, and you get a different structure. This is actually a rutile structure up here, that changes the structure here and gives you the enhanced activity. Okay. But so it's a combination of this exquisite joint density functional theory and the data here. But this gives you an idea of the kinds of things you can do with these reflectivity scans to actually understand what's going on in an important electrochemical process. Okay, so next effect we want to take into account. We can take advantage of the finite size of crystals or surfaces and interfaces to give us sensitivity, basically, to things that we're interested in. And there are other things we need to worry about or take into account that can affect the scattering. And where the basic idea, what you saw was a small change in the lattice spacing on that top layer, there it gave a big effect. Well, a big effect at the low scattering part. We're going to find that other small changes can also have measurable signals. And the first one I want to talk about is the effect of thermal vibrations. And one thing is that you all know is that we live at room temperature. We don't live at absolute zero. And it's much more comfortable room temperature. If things get too hot, it's uncomfortable. If things get too cold, it's uncomfortable. And what the effect of temperature microscopically, of course, is that things are vibrating around randomly. That there's the equal partition theorem tells you that there's, every normal mode has a half kT of energy, so on. And so every little vibration and stuff is just vibrating around with some random thermal energy. And so so up till now in our diffraction theory, we've been assuming the atoms occupy, precise, definite positions. When you think about it, well, every atom is probably, not probably, it's definitely just vibrating around its equilibrium position. It doesn't move very far, but it vibrates back and forth. And every time an X-ray scatters off, we basically take a quick snapshot of how it happened to be in that location. So we essentially are measuring the average positions about which the atoms vibrate. It is an ensemble average. So to take this into account, we just to be a little bit more careful in our calculations. So when we did our original calculation, we said that if I have the nth atom is of some type n, and whatever it is, and it's a position r sub n in the unit cell. So if I want to include thermal vibrations, I can define a new r vector, let's call it r prime, just to distinguish it, which is the previous equilibrium position plus a small displacement. And so this is going to be the vibration amplitude of the nth atom. So the actual position is the equilibrium position plus the little oscillation vector. But now I can just go back to my original formula and just plug this in where I used to have r. I plug in r prime, or where we have an r, make it an r plus u. And I can just plug it back into my expression where the cross section was r naught squared times a star. So all I have to do is plug this up here into the sums. And so this is a star. If I multiply things out, I'll get, here's my atomic scattering factors, here's my original, this is going to give me the Laue condition. And so this whole thing here is my previous answer. This new piece over here in the angular brackets is what's due to thermal vibrations. In this case, the angular bracket can, you can either do a time average or an ensemble average, depending on whether you're in equilibrium or not. That's a statistical physics question, but clearly you need to do some kind of an average. Normally, at this point, you can whichever you find easier, or that they're usually equivalent. That's a subtle detail you can write your PhD thesis on how to do that average. But to simplify the notation, right, because I've got Q and the two vectors here, what I want to do is take the magnitude of Q out front, and then I'll have two other scalars in here, but these are the components of these displacement vectors, which are parallel to Q. I'm basically going to take out the dot product, and the advantage of doing this is I now have all scalars here. I don't have to worry about the vector nature of the sum. It's just I have to be careful that this is just the component of the displacement that's parallel to the scattering vector. But then I can work with a scalar algebra instead of vector algebra, and again, for my simple math brain, this is much simpler. And then I can also take advantage of some mathematical true statements. If my distribution of fluctuations is Gaussian, which is quite common for a case, and even if it's not precisely true, it's almost always approximately true. And so it's a good starting place. If that's the case, then the average of e to the ix looks like the exponential of the average of the square. And this is important because if you think about the average value of x has to be 0 for a harmonic oscillator. It spends as much time in plus as it does in minus. This goes back and forth. And so if you think about it, it's not immediately obvious to everybody that this thing isn't 0. But for a Gaussian distribution, we can actually calculate it exactly. So I can just take this formula and evaluate this thing, that my x is just q times the difference of the u's. The q doesn't have anything going, it's just a number, so it pops out of the average. And I come up with this new formula here, where if I multiply out the square, I can rewrite this whole thing like this. And so now I find that this whole thing looks like terms here where this is the average, the mean square average of the vibration amplitude of the nth atom. This is the mean square vibration amplitude of the nth atom. So it's a very simple idea here. Here, there's a correlation between the vibrations between the two atoms. If there is no correlation, if they're just completely independent oscillators, this would be a 0, but e to the 0 is 1. So this term goes away. So frequently we'll just ignore this term. If I can't ignore it, I can always do a trick where I can write this term, I can add and subtract 1. And you're like, well, why would you want to do that? Well, if I do that and I add and subtract 1, my scattering cross-section became really simple again. It starts out, I get substituting all this stuff in, I get the sum of two terms. I get the one term, which is this top piece up here. And that's just my original scattering factor, or the scattering cross-section. With the substitution, that I replaced my atomic scattering factor by the product of the atomic scattering factor and this term right here, which looks like q squared times the mean square, or the average value of the square. So whatever this was, it gets reduced a little bit by the vibration, and for atom by atom. So I can just treat this whole thing as a new atomic scattering factor, so you have slightly less scattering in all of my delta functions. This other thing down here, so these are still delta functions. This other term down here is where the scattering went. All the scattering that went out of here had to go someplace. And this goes out into well, the first point is these delta functions are not broadening. So all of my Bragg peaks are still Bragg peaks, they're still delta functions, they just had their intensity reduced. So, by convention, and this term is usually rewritten as e to the minus m, and that's known as the Debye-Waller factor. Crystallographers use that all the time. But the key point is the scattering is still delta functions, but with reduced intensity. So the second term now looks something like this. I expect these correlations to be small, so I can expand the exponential so this looks exponential of e to the x when x is small is 1 plus x. So I have this thing minus 1 is just x, and I get this term down here. All right. So this is q squared times correlation. So I'm looking at the correlation between displacements on the nth atom to correlations on the nth atom. In the simplest case, they aren't correlated, so this is 0. If they are correlated, they're typically only correlated over very short distances. So that means if I have a thing where the correlations are small, that's like having a small crystal. So I expect the scattering to be spread out in reciprocal state, so that it'll be much broader than the width of the Bragg peak. So what I expect my scattering to look like is the sum of a very sharp Bragg peak and then a broad diffuse peak, which is this thermal diffuse scattering. And it's called first order thermal diffuse scattering. And if you, in principle, you can calculate all this by calculating the vibrational modes, the phonons, and doing detailed calculations. You can calculate these things and calculate what the thermal diffuse scattering is. In our case for crystallography, it gives you a very broad, smooth background, which may need to be subtracted. It's relatively easy to subtract because it's so broad and smooth. You can look at each Bragg peak and find the sharp part and then see the diffuse background. And it's typically done many orders of magnitude from the Bragg peak, so it isn't that big a deal to get rid of. It can be interesting in its own right, as it gives you direct structural information on the elastic waves or phonons in a crystal. Furthermore, if you think about it a little bit, if I go back to, well, hang on, it also, these elastic waves or these distortions don't have to be due just to thermal distortions. They could be due to strains or macroscopic effects or defects. So there's very similar formalism we're going to be able to apply to strain fields around defects or induced by other things. So that, this is just a displacement field, and we can apply it either to thermally induced vibrations or to other things. We'll talk about that in just a minute. Okay, one small complication is that we don't always have a single kind of a monatomic crystal. Most crystals have more than one element, so my unit cell structure factor gets a little bit more complicated. So I'll have a Debye-Waller factor for each atom in the unit cell. It'll have an atomic scattering factor, a Debye-Waller factor, and then a location vector. And these Debye-Waller factors are we calculated it using this expression here. If I convert it from Qs to wavelength in a crystallography tables, it will usually be coming into this formula where tables will actually use the B factors as for crystallography. So if you're, depending on the literature you're reading, you may see either an M or a B. They're the same thing, just the differences are using Q or lambda. But there's nothing actually very interesting there, but be careful in the literature, it can be confusing. Okay, we're almost ready to do an experiment there. We want to actually measure do a structural determination. We have to actually go measure the intensity from a crystallite. What we really care about is the number of X-ray scattered from these delta functions. We want to integrate these guys and find out the diffraction. So how can I get what's really coming to my detector, and how do I get back to my structure? Right. And so just recapping, we have the atomic structure, or the Thomson scattering factor here. This is the structure factor of the unit cell. Here's my delta function. You need to know how many atoms are in my unit, or in my crystal, the volume and the reciprocal effects in real space. This is a polarization factor we haven't talked about yet, but ignore that for the moment. The basic idea, I'm going to come in with a beam, X-ray beam that has a certain number of photons per square centimeter per second, and assume that it's monochromatic. It's going to whack into a sample. And I'm going to have a detector out here at some angle to theta, and I will measure the scattered intensity in photons per second at my detector. I'd like to then move my detector around, rotate my sample around, and try and measure enough information to come back and say, where are the atoms in my sample? Okay, it's got to be a little careful now. So let's assume that I have a perfect feed coming in. It's both perfectly monochromatic and it's perfectly collimated. That even in that case, we know that because I have a finite sized crystal or I have a surface, that while the scattered beam will still be monochromatic, it's elastically scattered, but it won't necessarily be collimated. that it doesn't have to all come out at the same kf anymore. So for example, we know that the width of the Bragg peak is inversely proportional to the number of atoms. So the Laue condition doesn't have to be perfectly satisfied to get measurable intensity. So in pictorially, what that means is I have Ki coming in, Kf coming out. The difference between these two is my scattering vector, Q. And normally, whenever Q is equal to G, that's the Laue condition, so there would only be a delta function here. But if I have a finite number of samples, this thing is a little broader here. So that when I translate my K over here, there'll be a range of Ks, Kfs, which satisfy this condition now. So there's going to be a range of things near the G value, and it's going to map out whatever's going on here. So different values of Kf will be allowed for a given value of Ki. And in particular, right, I can rotate my Kfs, and it'll take a little stripe across whatever so one is what's intrinsically there for the crystal, the other is what I actually measure with my beam. And so if I know that the magnitude of Kf is fixed, it's elastic scattering, but as I rock Kf here, I'll see this will trace out a circle. I translate it here, that circle comes through here. There. So when I just put up my area detector, what I'll see is a little streak, which is that, wherever Kf is, it comes through here, that's what I'll see on my detector. If you can also then, that will give you a range of Qs. If you look at it, that Q is actually going to go from here to here. So this Q vector actually shows up as a range of Q values that are being in there. And so I can be a little careful. If my detector, if it doesn't have position sense, it's going to have a big detector, it will integrate over all the Kfs. If I rotate my sample now, that basically rotates Ki relative to the Bragg plane, and so it kind of rocks Q back and forth. So I can, by rocking my sample, by having a big detector and rocking my sample, I can actually get all of the scattering, which is in this volume here. But that's what I care about. That's the area that I need to integrate over to get the total number of electrons. So the key thing is to integrate this whole thing, and I do that by having a big detector and rocking my sample to get the integrated intensity. Okay, there's another thing we got to be a little tricky about. We want to compare that integrated number to my structure factor. So there are two components to this integration. One is integration over orientations of the spinal wave number vector, and an integration over orientation of the crystal. So let's compare these mathematically. What do we have to do? We'll take the integration over Kf first. Okay, so I'm going to walk you through the algebra here, but it's only the answer that matters. All you have to do, so watch this and then just trust me, I guess. So let me define a unit vector, which is basically in the direction of the Kf. So I get that by dividing Kf vector by the magnitude of Kf. And so what I want to do is integrate over orientations of that final director, or some the delta functions. Now remember the delta function Q is just Ki minus Kf. Now we're going to do some math tricks. If I can, there's a mathematical property of the delta function is that this particular integral is just K over 2, a true statement. That means if I can both multiply by this function and divide by this, and that's a 1. I'm going to take my original expression here, that's this over here, multiply by 1. If I rearrange things, just flip things back and forth, I come up with this expression down here at the bottom, which then collapses the integral, leaving me with this final result. And my original integral now I've recast into this form here, where now the angle from the dot product is the angle between the incident wave vector and the reciprocal lattice vector. I can substitute that back into my original delta function expression here, and get something that looks like my whole delta function here, integrated delta function, is now this thing. If I now take that form and I want to integrate over, now rotate the crystal, I do another integral over this theta variable. And again, I do some algebra, don't worry about it. But the answer is I get something that goes like 1 over k squared and 1 over sine 2 theta. So the differential scattering cross-section, when I've integrated over both orientations of the final wave vector and over orientations of the crystal, collapses down to this pretty simple formula here. Two different versions of it. And I got my Thomson scattering factor, I got my structure factors, I have this is the number of atoms in my crystal. I can either express it in terms of the reciprocal space volume and k, or in terms of real space volume and lambda. And then there's 1 over sine 2 theta. Okay, so this is a direct link now for what I measure, the scattering cross-section. Through this formula, I can get directly to my structure factor. Okay, so now I know how to get from in a perfect crystal, how to do a measurement, but most times we don't have perfect crystals. In fact, we're kind of spoiled by the semiconductor industry, and the idea that we can ever have perfect crystals is due a lot to our ability to grow silicon and so on. And more recently, a molecular beam epitaxy technique is how we can actually get really perfect crystals of other elements and so on, and mixtures. But most of the time we don't get perfect crystals. And in fact, the most common thing is if you just picked up a piece of copper or something and looked at it, it would, no, it's not a perfect crystal. What it really is a collection of an enormous number of little tiny grains, each of which is a crystal. So a typical grain might be of order a micron. So if you have a piece of copper wire or something, you have a huge number of little tiny crystals, but they're all kinds of sizes, shapes, and orientations. And so, but we can go to the other limit and say my sample, instead of being one crystal, is just a powder. And a powder means essentially an infinite number of crystallites that are oriented completely randomly and mixed up. So in the simplest case, they all have about the same size, and we don't need to worry about their shape. It's just that every possible orientation is there, and that there's no preferred orientation. If you then, if we go back to the idea of, if you consider a specific reciprocal lattice vector specified by the h, k, and l, that will still be true. So if I now think about my sample as I rotate it, no matter what orientation I pick, there's always some crystallites that are at the Bragg condition. And so if you think about it, there's a sphere of scattering. Okay? So that in an ideal pattern, right, if I have a uniform distribution of orientations, the directions of each of the g vectors for a specific crystal are uniformly distributed on the surface of that sphere. And there are always some of them that have the correct orientation for Bragg scattering. And that's why we like powder diffraction. You don't actually have to orient your crystal. But then you got to make the question that we would still like to do crystallography. Okay? And so if you now think about what's going to happen, you're going to get cones of scattering and so on. These are called the Debye-Shearer cones. So your diffraction pattern, instead of looking like spots, is going to look like rings. Okay? And so again, there's a little bit of geometry to convert from the distribution you measure in those, they're called the Debye-Shearer rings and the Debye-Shearer cones. What you really care about is the number of grains that are in the correct orientation to reflect for a given orientation. And that we can get from the following geometric construction. And again, the answer is what's important. The geometry, you can go back and figure out that it's all straightforward or like tedious. That's so that in the end, it's just a formula for you. No. But there's one more complication for powder diffraction, and that's that the multiplicity of the peak. So I assume that they were all the same. If you think about, for example, a 1-1-1 reflection, there's also the -1-1-1 reflection. There's the 1-1 -1, the 1-1-1, -1-1-1, and so on. They all have exactly the same length, and you can't tell the difference in the grains which one you're looking at. So that's called the all the permutations that you have that put you on the same sphere. All right, so we have, when you're kept looking at the intensity of your ring, you have to take into account the multiplicity, how many different G values actually contribute to that ring. And that's known as the multiplicity. So for a simple example, an H00 peak multiplicity is 6, because the in a cubic crystal, plus or minus H, plus or minus K, and plus or minus L all diffract the same value of 2 theta. So then we do a similar argument to the one we before about the cones and so on. And the question is, what is the circumference of the circle? And it's going to be proportional to sine 2 theta and so on. And again, you now have to put in all of these correction factors. So we had, we've already talked about the number of grains on them. This is the multiplicity. There's a fraction of the ring. This is the Lorentz factors we can calculate. And there's an L factor which has all of these corrections now, which are just geometrical corrections which you can put in and to actually calculate your data back. And the whole idea is to get from your observed data back to what is that fundamental structure factor of the unit cell structure factor. And in the end, you can then write down these, when you can, the squared structure factor can then be retrievable directly from powder diffraction data using the following kinds of ideas. And so, you know, these are all things you can just calculate. So the ratio of the intensities directly gives you the ratio of the intensities here. So if I normalize, if I know the value of any one of these, I can get the values of those, or I can at least get the relative values of all the peaks. Okay, these just, the L values and the polarization factors come only from the geometry. Okay. But this is the key idea, is that these ratios, these are measured things. This is the intrinsic quantity you want to know. These are correction factors from geometry. But then that allows you to take data like a powder diffraction pattern. And many of you used lab sources and stuff and measured powder structures. And this is a particular material we looked at a long time ago called European titanate. Okay? And this is what a diffraction pattern looks like that out of a powder diffractometer, or that you can integrate as you scan out. You see it's usually plotted as a function of 2 theta. And here's the 100 peak, the 110, 111 in the indexing and so on. From these intensities, we can then work back and get the structure factor. Okay. Nobody's yelled at me yet about questions. And tonight, sorry, I apologize. I forgot to look over and see if anyone's waving at me or hollering. Okay. But I guess I'll stop there for today. Next time, for the last lecture tomorrow, we'll go back through and talk about thermal diffuse scattering in detail. The analogy then takes us directly into strained crystals. So for the structural materials guys are very interested in. Small angle X-ray scattering, and then a final example of an in situ growth experiment, which uses sort of all of the above. It's how we looked at the nucleation growth of perovskite materials, the europium titanate, in fact, using pulse laser deposition. And so that's tomorrow. I guess I'll stop, and I should have done this a long time ago. I apologize for other questions.
Okay, if there's any questions, now is the time for you to go to it. In the meanwhile, I'm gonna tell you that I sent yesterday the presentations of lectures 1 and 2, and I'm going to send today the lecture 3. I wrote my email again in the chat, so if you're not in my list of contacts, or if you're not receiving this information, please feel free to write to me and I'll send you right away. Well, Joe, interesting how it changed from the crystal. We tend to think about single crystals because it's the easiest way to imagine it somehow. But it goes, you know, it's good to know that, you know, the real samples are quite different, and we need to move from that picture and go to the powder. That is what, you know, mostly the samples we have.
Yeah, a lot of the students probably will do some powder diffraction, right? The technology is, I mean, the surface experiments require a synchrotron usually for the intensity, but powder diffraction, you can get a tremendous amount of information and then come down more and more detail with the more and more powerful machines to look at things. So I think you know, some of these, you know, because of the PREM and the emphasis on electrochemistry, some of these surface effects are really important. And we can actually see where the atoms are at these interfaces. It's a lot of work, but we can actually get, you know, real numbers as with, and just actually sort of astounding level of, you know, I don't know, it always amazes me that we can see where the atoms are. It's still amazing.
Yes, it amazes me too. How can we characterize the materials with the different techniques? It's really a wonderful thing. And I you know, I appreciate this explanation between the simplest thing and the more complicated thing, and how we get some types of information from one instrument to the other, because we usually, as it says, use X-ray diffraction, powder X-ray diffraction, to characterize if we have a crystal or not, or those kind of things. But with the synchrotron, we have been able to go further and look to the details.
Yeah. I think the new techniques of the spectroscopies that, you know, you've been studying there's been a couple workshops on those already, right? And so it's really new things, and some of the, I guess I should probably put I'll add it tomorrow also on these pair distribution function measurements, very similar to one of the things I'm talking about tomorrow. And I think that's sort of the more local structure probes. So that XF is a spectroscopy version, but there are also some scattering versions that are you know, quite powerful. But you know, they require a lot of big data and computers and so on. But that's sort of the next level of complication, right? Is to,
yes. Well, is there any questions? Remember, you can write emails if you have any questions later when you review the information. Well, Joe, I think we're okay for today. I'll be sending the documents and see you tomorrow morning.
okay. Great. It's great seeing everybody again.
Bye.
Okay. Bye-bye.
See you tomorrow.